Hey guys, this is the video on Euler and graph problem. Some citizens of Konigsberg were walking on the strand beside the river Pregel with its 7 bridges spanned. "O Euler, come and walk with us," those burghers did beseech. "We'll roam the 7 bridges o'er, and pass but once by each." "It can't be done," thus Euler cried. "Here comes the QED. Your islands are but vertices, and 4 have odd degree." William T. Tute. We begin our journey into the nature of computation with a walk through 18th century Konigsberg, now Kaliningrad. As you can see from figure 1.1, the town of Konigsberg straddles the river Pregel with 7 bridges, which connect the 2 banks of the river with 2 islands. A popular puzzle of the time asked if one could walk through the city in a way that crosses each bridge exactly once. We do not know how hard the burghers of Konigsberg tried to solve this puzzle on their Sunday afternoon walks, but we do know that they never succeeded. It was Leonhard Euler who solved this puzzle in 1736. As a mathematician, Euler preferred to address the problem by pure thought rather than by experiment. He recognized that the problem depends only on the set of connections between the riverbanks and islands, a graph in modern terms. The graph 1.1 corresponding to Konigsberg has 4 vertices representing the 2 riverbanks and the 2 islands, and 7 edges for the bridges, as shown. Today, we say that a walk through a graph that crosses each edge once is an Eulerian path, or an Eulerian cycle if it returns to its starting point. We say that a graph is Eulerian if it possesses an Eulerian cycle. Now that we have reduced the problem to a graph that we can doodle on a sheet of paper, it is easy to explore various walks by trial and error. Euler realized, though, that trying all possible walks this way would take some time. As he noted in his paper, translated from the Latin, as far as the problem of the 7 bridges of Konigsberg is concerned, it can be solved by making an exhaustive list of possible routes, and then finding whether or not any route satisfies the conditions of the problem. Because of the number of possibilities, this method of solutions would be too difficult and laborious, and in other problems with more bridges it would be impossible. Let's be more quantitative about this. Assume for simplicity that each time we arrive on an island or a riverbank, there are 2 different ways we could leave. Then, if there are n bridges to cross, a rough estimate for the number of possible walks would be 2n. In the Konigsberg puzzle, we have n equals 7, and while 27 or 128 routes would take quite a while to generate and check by hand, a modern computer could do so in the blink of an eye. But Euler's remark is not just about the bridges of Konigsberg. It is about the entire family of problems of this kind, and how their difficulty grows or scales as a function of the number of bridges. If we consider the bridges of Venice instead, where n equals 420, even the fastest computer imaginable would take longer than the age of the universe to do an exhaustive search. Thus, if searching through the space of all possible solutions were the only way to solve these problems, even moderately large cities would be beyond our computational powers. Euler had a clever insight which allows us to avoid this search completely. He noticed that in order to cross each edge once, any time we arrive at a vertex along one edge, we have to depart on a different edge. Thus, the edges of each vertex must come in pairs with a departure edge for each arrival edge. It follows that the degree of each vertex, that is, the number of edges that touch it, must be even. This holds for all vertices except the vertices where the path starts and ends, which must have odd degree unless they coincide and the path is a cycle. This argument shows that a necessary condition for a graph to be Eulerian is for all its vertices to have even degree. Euler claimed that this condition is also sufficient and stated the following theorem. Theorem 1.1. A connected graph contains an Eulerian cycle if and only if every vertex has even degree. If exactly 2 vertices have odd degree, it contains an Eulerian path but not an Eulerian cycle. This theorem allows us to solve the bridges of Konigsberg very quickly. As the poem at the beginning of the video points out, all 4 vertices have odd degree, so there is no Eulerian path through the old town of Konigsberg. Beyond solving this one puzzle, Euler's insight makes an enormous difference in how the complexity of this problem scales.